All right, good morning, everybody. We'll get started this morning. Just a couple announcements. Generally through the course, I'll post announcements up on in the lecture slides area. Some of you may have seen today's announcements. One of them was just to be aware for lab that you have to wear, and you should have taken quizzes on this already too, but you have to wear pants and closed-toed shoes. And that shoes have to have a back on the heel and whatever. So make sure when you show up in lab, you have those things with you. Some students bring, pack a pair of sweatpants in their book bag just in case they forget. And then the other announcement was, also you need lab coats for lab. Has anybody not gotten their lab coat yet? I'm guessing a lot of people probably still need to get their lab coats. Over at Celeste, probably want to get it today because I think a lot of you guys probably have lab Tuesday morning, 8 a.m. And I think they're going to want lab coats at the start of lab on Tuesday. So you might want to make sure you try to get those today if you haven't gotten them yet. And then the other announcement was about all the homework assignments, just kind of a reminder of the lecture assignments, like the alternative lecture tutorial assignments are an alternative assignment for lecture attendance, which we start taking next Wednesday. I put one together for today's lecture just so that if you guys happen to like the tutorials and want to use them to go along with today's lecture, that the alternative assignment is there. So the tutorials, like you can check it out for today's assignment. There's no harm in clicking the link to start the assignment. You won't be penalized if you try an assignment and give up on it or don't finish it. And all of the homework assignments, there's never a submit button. Anytime you do work, it's live saved. Those alternative assignments, again, it's an alternative lecture assignment. So next Wednesday, if you come to class, I'll have a quiz that you do at some point during class. It's just going to be, are you here? Yes. And then you submit it. You get your 5 recitation points, or excuse me, your 5 lecture points for the day. And then if you miss lecture, then you can go do that alternative assignment. The only issue with the alternative assignment is at the very end, you get a little completion screen. There's a snapshot in the notes a few pages back in the slides. But you take that completion page and you upload it to the alternative assignment for that lecture day. So like if you miss lecture next Wednesday, that's lecture 3, you would do alternative lecture assignment 3, and then upload the screenshot of that to the alternative lecture assignment in Carmen, and then eventually I'll put the grade in for you manually. It'll take a day or so for me to put those grades in. Hopefully come to class. I think it's gonna be easier to get the points if you just come to lecture. I know it's early, so if you'd rather do the tutorials, or if you find them to be valuable and useful, you can certainly do those. For those who choose to do the tutorials and not come to class, that's fine. That's a great approach too, and I think it'll help you prepare for exams down the road. Okay, so with that, generally most of my announcements I'll just put up on that feed on the lecture slides, and I probably won't give them as often in class, but since I started a moment early, I figured I would talk about that information today. One last note would be reading assignments. Those are just linking you to the e-text access and the covered sections for the day. There's no required work within the reading assignments. The only required work for credit in the class are the post-lecture assignments. First one of those is due Wednesday morning before class, 8 a.m. Small penalty if you're late. So if you forget about this next Wednesday, you can still get a 1% penalty per hour late, and you can still earn a lot of the points even if you're getting this done Wednesday at like noon. And then make sure you set up your e-text access, Pearson access to be able to get into all of those assignments. There's a bunch of help files in the started term tasks. There's office hours for the tech support specifically for Pearson through Zoom, I believe, but check those office hours out. Okay, so with that, we're gonna talk about roughly the first half of chapter 1 here today. And the class is going to start off kind of very basic. I mean, almost everybody has had, you all had to have chemistry to get into the course in high school or some sort of advanced physical science class. So I know we've all seen a fair bit of chemistry before. A lot of the topics that we're going to see are review in nature, or at least some of the topics start off as review, and maybe we'll get a little bit deeper into chemistry as we go throughout the semester. So if over the first lecture or two, you're like, oh, this doesn't seem hard at all, just stay caught up, stay current, kind of know eventually we're going to build up in pace in this class. And then at the midterms, you're going to be kind of required to have the vocabulary down, the ideas down, the content down, and be able to solve just about any of the problems from the chapters that we're covering. So sometimes the material seems easy at first glance, but then when you really get into the heart of the problems, they start to get a little bit confusing if you haven't done a bunch of practice problems. So make sure you do enough practice, enough homework, enough self-assessing of your strengths and weaknesses throughout the class to kind of be confident heading into our exams. Okay, so with that, let's just introduce chemistry, or the idea of chemistry being the study of matter being comprised of atoms as our main building blocks. And then a given atom is of a particular element, where elements are defined by their nucleus. We get into some of the discoveries of the subatomic particles like protons, neutrons, electrons, that discussion in chapter 2. So we'll talk a little bit more about how you characterize atoms by their proton count in the next chapter. But I think we've all seen and worked with the periodic table and know hydrogen's the first element, has 1 proton in its nucleus. Helium's the second element, has 2 protons in its nucleus. And as you go throughout the periodic table, what's making each element different from each other are those number of protons. Here in chapter 1, I like to kind of stress that we'd like you to recognize name to symbol or symbol to name. Like if I give you Na, I want you to know it's sodium. And so the first block of elements, and we get into the periodic table a little bit more in terms of discussing it in chapter 2, but the first group are the alkali metals. I think you probably remember that. So the lithium, sodium, potassium, rubidium, cesium group. We just want you to know name to symbol, symbol to name. You don't have to remember the placement on the periodic table. You don't have to remember like how to order the elements. It's just recognizing the symbol or name if we use either one of those. The next group's the alkaline metals. We'd like you to recognize beryllium, magnesium, calcium by name or symbol down that group. And then kind of across the main group on the boron, carbon, nitrogen, oxygen side of the periodic table, again, just name to symbol for the first, what we generally say is the first 4 rows of the periodic table. So kind of through the potassium row. And it's, again, not memorizing the placement or the order and reconstructing a periodic table. You always get a periodic table with your exams, but it always just has the symbol. So if we use a name, we just want you to know the name that goes along with it. You know, so phosphorus is P, not potassium. Potassium is K. Sometimes if you haven't seen chemistry in a while, it's useful just to kind of go through the more useful elements that we use. The first 4 rows plus some of the other groups, like the alkali groups used a lot. The halogen group is the fluorine, chlorine, bromine, iodine group. You see like iodine in a lot of examples, so that's a pretty obvious one. The noble gases are useful to kind of point out, and we'll talk a little bit more about them later today too, just on how they're stable gases in their natural existence at room temperature. So helium is stable to exist as a single atom in the gas phase. And the noble gas group is the only group of elements where that's the case. Every other group is either going to partner up like H2 or O2 or N2, or it's going to form some sort of solid or liquid, like say iron solid, where the atoms bond together through metal bonding. Okay, so we just want to know the basic name to symbol, symbol to names for some common elements. A few other larger elements that we use just a fair bit in examples are like silver is Ag. And some of these are the symbols and names that don't match up alphabetically. So silver Ag, I think probably most of you guys know gold is Au, but that's gold, mercury, tin, lead. So those are some of the more common elements that just don't match up very obviously to their name and symbol. Sometimes it's useful to remember copper is the Cu and cobalt is the Co, since they both start with Co, that copper is Cu. And so then what defines a compound is when we take 2 or more elements and somehow chemically bond them together. Now, we're not introducing too much about chemical bonds here in this chapter. You could maybe remember ionic bonds is like Na plus, Cl minus being attracted together through that electrostatic force of attraction. You probably remember that. You probably remember like H2O2, the bond between those atoms is like a covalent sharing of electrons. And so there's covalent bonds. I already mentioned like iron has what we call metallic bonding. You may have not talked about metallic bonding that much, but anything that's stuck together has some type of a bond or some type of an interaction that's holding those atoms together. And so when it's a chemical bond that's linking 2 different elements together, we call that a compound. So like O2, molecular oxygen, 2 oxygen atoms bonded together would not be a compound because it's just one element. And so just being able to write a formula like O2 doesn't mean it's a compound. That's still actually what we call an element. So if I say N2, what is that? You would actually say it's the elemental form, it's the element nitrogen. It's just in its natural form that we encounter at room temperature on Earth. We then like to discuss kind of very generally in chapter 1, the difference between chemical and physical reactions. And one of the confusing parts here is that one of the types, like a physical change would be melting or boiling. So you take water liquid to water solid. So one of the things that sometimes you'll see is if I write this water, say liquid, boiling to water gas, one of the really confusing aspects of that change is that I can write it like it's a chemical reaction. I use the reaction arrow, I write the before and after, but it's really just a physical change. It's really not a chemical change. A chemical change requires a change in the actual nature of the compounds or the substances that are present. So that's what, I think it's a bad example to show. If I write the reaction out and say, is that a chemical reaction? I feel like I'm tricking you, but it's just a physical change. So a physical change is a change of state, a change of pressure, a change of conditions, and then a chemical reaction is a change in the chemical nature, a change in the actual bonding that's present between those elements. So chemical reactions involve the change in chemical bonds. Physical reactions just the change in either phase or temperature or pressure without changing the bonding. Physical changes are sometimes more easy to recognize because you can go back and forth on them. You can boil, and then you can condense back to what you started with. If you think of a chemical change, like the cooking an egg, for example, you're not going to be able to put the egg from its cooked form back into the shell, back into the liquid form of the egg before it was cooked. And so that would be some chemical changes. Even if we don't know what the chemical changes are, there's something going on as you cook an egg that's changing the nature of the molecules in that, on all the substances in an egg. We also like to define the difference between intensive and extensive properties. And I think the main idea here is an intensive property is quantity independent. So that's the sort of main idea. Intensive property independent of the quantity, and therefore it's characteristic of the substance. So an intensive property is like a boiling point. It's like a density. So if you have water, you have ethanol, or you have benzene or glucose, all these substances have their own melting points, their own boiling points, their own densities, their own intensive properties. So the intensive properties are generally the ones we think of as being characteristic of a substance, different for different substances. And then extensive properties are ones that are just quantity dependent. So they're just properties that depend on how much of the substance you happen to have and how much of a substance you have. Like I can have 5 grams of glucose or water or ethanol. And so I can have 5 grams of anything. It doesn't tell me something specific about the substance. So that's just a quantity dependent value. And so mass and volume, heat is actually another one. How much heat a substance contains is just dependent on how much of the substance there is. And in some of these, there could be a link to an intensive property. Like if you know you have 5 grams of a substance, if you know its density, you can then relate that to then how much volume you have. You can relate mass and volume by the density, but the actual value of the mass itself is extensive. The actual value of the volume is extensive. The relationship between the two, the density, is intensive or characteristic property. Let's look at a couple examples here. So let's try to characterize these properties as intensive or extensive properties and then try to classify them as a physical or a chemical property. So the first one, 30 mils of water. Pretty obvious that that's the extensive property. And so that's our extensive property example. So just having the amount of the water that's present, that's an extensive property. And then there's no change going on. So you would just think that's like a physical property is how much you have. You have more. You're not chemically changing what's going on if you have more or less water. I don't even know if that's so much a physical property, but it's definitely not a chemical property. Now the sample has a density, so water's density is about 1 gram per milliliter, and it's slightly variable by temperature if you get really precise. But liquid water is around 1.00 gram per milliliter in terms of its density, and that's the characteristic of water. Ethanol is different, it's a little bit lower, it turns out, but most substances have their own different and characteristic densities. And so, of course, this is the example of the characteristic intensive property. So it doesn't matter if you have 2 milliliters of water or 10 milliliters of water, the density of the sample is still the same. The density is still 1.00 grams per milliliter. So you can have 2 grams of water, then you'd have 2 mils of water. So those two properties are extensive. The relationship between the two is intensive and characteristic. Because if I took a different substance, if I took ethanol, which has a density more like 0.8 grams per milliliter. And if I took 2 milliliters, I don't have 2 grams. So it's dependent on the substance, that density. So an intensive property. I don't think this is a chemical property yet either. Density, to me, just seems either like a physical property, or maybe for some of these properties, it's hard to characterize, is it physical versus chemical? When we start thinking of a change that's going on, maybe then we can think of physical versus chemical change. So boiling point is one that involves a change. When we boil, we go liquid to gas. And so for water at standard atmospheric pressure, that's 100 degrees C. And so the boiling point of water, this is a characteristic property. Think of it this way. Does that property change if I have more or less water? And it's the same. If I have a milliliter of water or a gallon of water or a lake of water, the boiling point's still 100 degrees C. And so that is quantity independent, so intensive. And then the change itself, even though we can write it as a chemical reaction, we still think of this as a physical change. So physical change because we're not changing the bonding between the water molecules, between the H2O molecules themselves. So sometimes this is obvious, sometimes it's not. But when you have water, like H2O, liquid, there's a picture of this later too, but you have individual molecules that are all bouncing around each other in liquid water, have some attraction for each other in the liquid water, then we break those forces of attraction when we boil, we have separated water molecules. So we still have H2O molecules in the gas phase, they're just far away from each other. We bring them back together and condense the water molecules, they then stick together, but still become independent water molecules, to two hydrogens and oxygen floating around independent of each other in that liquid sample. So we're not changing the bonding between the H and the O's in water when we boil or condense. Now, atomization is where you break all the bonds in a substance. So if we were to take H2O, doesn't matter the phase, but let's say it's liquid, and break this apart into gaseous hydrogen atoms and gaseous oxygen atoms. Kind of hard to imagine how this would happen, but if we were to atomize water, you can say, well, how much energy would that take? It turns out for water, it's 969.2 kilojoules per mole. I know we maybe haven't defined kilojoules. It kind of comes up a little bit in this chapter, a little bit more in chapter 5, but it's just a measure of heat. And so the heat per mole, we also haven't introduced the mole. A mole is a quantity unit, so it's heat per mole. So this is a ratio of the heat it takes per quantity of substance. And so it doesn't matter, therefore, how much substance we have, this property is going to be the same. So this is an intensive property. So it doesn't depend on how much water we have because the quantity is the heat per quantity. So we can have a little bit or a lot of the water, the ratio of the heat it takes per quantity of water is still the same. So an intensive property. And I just wanted to use this as a really obvious chemical change that's taking place because we're breaking those chemical bonds. So this would be a chemical change. And I do think there's a few aspects like the unit mole we'll see later a little bit more, the unit kilojoule we'll see more later. So if you're looking at those units and saying those seem confusing, we'll talk about those more later. So don't feel like we're introducing those terms so that you really need to know them yet. So we'll talk about the mole more in chapter 3 and heat more in chapter 5. Let's talk about some basic ways that we can sort of classify matter. So the composition of matter, we could have atoms of a given element. All these boxes here are actually looking at gases. And then we could make a bunch of different pictures, though I don't think we will. Maybe we'll try to think of what liquids and solid pictures might look like. But this box is looking at if I had an element that existed as a single atom in the gas phase, what would it look like? Well, it would look like this box here where we just have atoms. Maybe these are things like helium atoms that are bouncing around whatever container they're in because they're gases and these particles are in motion. We talk more about gases specifically in chapter 10. But this is a picture of what we would have for gases. So an example here would be our noble gases. Because there's no other group of elements that exists as monoatomic, single atom gases at room temperature. So any other element, if we had a solid, I guess I could maybe draw a quick picture. If we had a solid, the picture would just be more like this. The atoms would be more aligned together. So this picture here, if we said, well, what does this look like here? This would look like an atomic solid, where the atoms, instead of floating around the container, are more confined and more trying to show that they're bonded together somehow. If we had a liquid, I don't think I'll show this, but I'll think what I might have is just randomly drawn spheres that are closer together. So, and then probably having a layer then above them that is empty. So a liquid, unlike a gas conforms to the container. A liquid would be confined to the volume it's occupying just for the liquid sample and not necessarily the whole container. And then the atoms wouldn't be so locked together. They would just be in like kind of random motion. We'll see a picture with water where for a molecule that might make a little bit more sense in the very next slide. We can then have molecules of an element. And there's some examples of molecules or of elements that do this. These would be things like H2, N2, O2, et cetera. So those are some examples of elements that exist as gases at room temperature and then would exist as molecules at room temperature. So a molecule is where we take two atoms or more and just chemically bond them together. And specifically, it actually has to be a covalent bond. We'll talk briefly about this as we go, but like NaCl, sodium chloride is ionic in nature, and we tend not to call NaCl a molecule, but that gets a little bit in the weeds. We tend to think of molecules as being atoms that are held together by a covalent bond. Now, this gets to the point where we haven't defined covalent bonding as like a chapter, as a unit yet, so it's kind of hard to really look at something and characterize, is it covalent, is it ionic? But the really simple way to know, just without knowing a whole lot about covalent versus ionic bonding, is that if you take a non-metallic element like hydrogen and then the right side of the periodic table, when those atoms bond together, they tend to form bonds together covalently. And then if you take a metal and a non-metal together, like sodium and chlorine, like potassium and bromine, they tend to form the ionic compounds. So metal, non-metal, left side, right side, left side except for hydrogen. If you take left side, right side, metal, non-metal, think ionic. And if you take all non-metallic elements, think it's going to be that covalent type bonding. And so then there's actually a range of, let me rewrite F2. There's only a few different atoms or elements that form the molecular compounds with two specific atoms. So H2, O2, N2. But we also have F2, fluorine, Cl2, chlorine, Br2, bromine, and then I2 for iodine. So those all form these diatomic molecules, so two atoms, that are bonded together in their like most commonly formed state at room temperature. So you're going to see those 7 diatomic molecules a fair bit. And so then that's the natural form of those elements at room temperature, looking like molecules where two atoms are bonded together. So now we look at this again, just from kind of the last slide, is I call this a molecule, but not a compound. But I could also call it an element, because there's only one element present within this box. So like, let's say this is defined as a nitrogen atom. So then this box here would be elemental nitrogen. So elemental is what I'm trying to write there. So elemental nitrogen. I should write less. I know everyone hates my handwriting. I should just like say it and not write it. But so I'm just trying to say that you can call the second box there, you can call it an element, you can call it a molecule, you just can't call it a compound. You also can't call it, what we haven't seen yet, a mixture. So you only have one thing present, so it's not a mixture. The next one shows molecules, because we have two different atoms shown. Now, whenever you see different shading or different colors, that's meant to imply different elements. So when you see a purple sphere with green spheres attached, that's meant to imply that you have two different elements that are present. Maybe this is something like NH3, which has the 3-to-1 kind of ratio we would see here. Maybe it's something like BCl3 or some type of compound where we have 3 of one element, 1 of the other, bonded together. You don't have to know anything about geometry yet or what these molecules would look like chemically or how they bond together. That's a much later topic in the class in chapters 8 and 9. The thing we can say is you have a molecule, so you have elements that are chemically bonded together. And so you have a molecule, and then you also have a compound because there's 2 or more elements that are present. So we can call those both molecules and compounds or molecular compounds. And then lastly, you can have a mixture of any and everything in between. You can take molecules and elements and atoms and mix them together and then have what you have, what we call a mixture. So you can take a mixture of just about anything where they mix together. And so we can classify having 2 different substances or 2 or more different substances present as a mixture. And we'll have a slide in a couple moments that tries to get at, is the mixture heterogeneous or is it homogeneous? Is it the mixed equally throughout, that's homogeneous? Is it not mixed equally? There are phases. Is it like oil and vinegar and it's heterogeneous and you have different phases present? This mixture here would look to be homogeneous because it's completely random. If you also think about the nature of gases, which again, the topic later in the class, so we'll talk more about it, but gases are just particles in random motion. So if you mix together random gases, they're just in random motion, so they're going to have to be homogeneous. It would be hard to imagine a gas separating into layers like you might imagine oil and water doing. So let's look at a picture that just kind of shows us at kind of like an atomic level, the difference between water vapor, liquid water, and ice. And so let's start with ice. So ice just shows our water molecules that are very ordered. So you have water, another water that's present. You have the electrostatic attraction of slightly positively charged hydrogens and slightly negatively charged oxygens. You may not have learned that, maybe you did, but water, we'll learn this later, or reinforces if you've already seen this later, that water has these dipoles that's making the oxygen partially negative, the hydrogen's partially positive. So then you can sort of imagine the stacking of these waters on top of each other, and they have these electrostatic forces of attraction of those partial positive and negative charges. And so that's the attractive force that holds water molecules together, but that's a topic for chapter 11. So hopefully just planting a seed for later of when we'll talk about that nature of the interaction between water molecules. But in liquid water, that's the electrostatic force of attraction that's holding adjacent molecules together. And the water molecules are also kind of shown to be a neat, ordered, and almost in no motion. But of course, this solid would still have the atoms moving, just not really fluidly. And so the atoms are never completely not in motion. Even if you go down really, really cold, they're still going to have some motion about them. But they're just closer together, they're not tumbling around each other. So then you melt, then the liquid water molecules tumble and no longer are held in place and constricted to move just slowly. They can move more rapidly relative to each other, but they're still held together by a force of attraction. There's still like a phase, there's still like a layer that holds them together as a liquid. And then if you can break that force of attraction, if you can break that surface and boil and start having bubbles form, you can then imagine water vapor forming where the water molecules are now just far separated from each other. So you just go from water being relatively close. Interestingly, the water molecules in ice do a really weird thing, which most substances don't do, where the water molecules in ice actually get further away than they are in liquid water. So in liquid water, the molecules actually get a little bit closer together. That's why ice is less dense and floats on liquid water. It's a really weird property. But then when you vaporize, molecules move very far away from each other, and because they lose that force of attraction. Okay, so hopefully just developing and reinforcing an atomic picture into what solids, liquids, and gases kind of look like. And we're still thinking of the water molecule being there before and after. So the water molecule isn't changing through this process, it's just changing the form it's in, or just changing the environment it's in. So how we can go through like a thought process of how we can classify matter. We have this flow chart here. This flow chart's kind of hard to go through at first because some of the questions we can't just directly answer by looking at a substance. Like we look at, like if we take a water example, or what we think is water, it's liquid, it's clear. Do we know just by it being clear that it's water? Of course not. It could be any other, it could be ethanol, methanol, or any other liquid that happens to be clear. But the first question you usually think about when you classify a substance, does it look homogeneous to the eye? So the first question here of, is it uniform throughout? This is usually something you can look at a substance and see, does it all look the same? Do I see a solid layer and a liquid layer? Do I see little specks of solid floating in a liquid? Can I see something that looks like it's heterogeneous in nature? And you can usually tell one by eye, so you can usually use your eyes to answer this question here. And if it's heterogeneous, this is like where you see like an oil and vinegar layer. You can clearly see that. You can see like red solid and a blue solid. You know there's two different substances present then if you can see different specks or different liquids and solids mixed together. So if you have a heterogeneous mixture, you know you have 2+ substances that are present. and they're just not present uniformly. So I'm saying 2 plus substances that are present to be that heterogeneous mixture that just aren't mixed randomly. And so then if you have your sample, let's say it's water, so, or let's say it's a liquid sample that looks like water, so we're just picturing a clear liquid. Now, is it salt water, is it sugar water, is it pure water? You can't answer the next question, does it have a variable composition? You can't answer that with your eyes. Like, you need to know something chemically, so you need to know something about this question here to be able to answer it. So you can't just look at a sample, like you'd never be able to look and be like, is that, like what is mixed in that water? Without knowing something about how that sample is prepared, you would never know. So you can't just look at a sample and ask and answer the question, does it have a variable composition? Now, let's go to the box right above it, though, where it says homogeneous. Homogeneous would be, if I have a liquid water sample, I could call it homogeneous. It doesn't mean it's a homogeneous mixture. Like, water appears the same throughout, so it looks homogeneous. It doesn't mean it's a homogeneous mixture. To have a homogeneous mixture, I have to know it has a variable composition. So a variable composition would be, I either put my molecular goggles on, look at the water sample, and then I can see water molecules and I can see ethanol molecules. So if I can imagine chemically looking at the sample, or if I knew somebody poured water and ethanol or whatever together, I know then it's a mixture that contains 2 substances. So if I know 2 different things were put together, then I know it's a homogeneous mixture. So if I can see 2 different things that are present, if I can see 2 different molecules, with my, again, molecular goggles, if I have a atomic view picture of the sample, this is like the previous page here of being able to say, or this page here, it's like the variable composition is seeing these 2 or 3 different things that are present inside the box. Again, you would never be able to look at a gas sample and see that with your eyes, but with some sort of molecular tools or just a box, or knowing that, oh, I put helium, oxygen, and ammonia into this gas mixture, then I know I have a mixture of those 3 different substances. Okay, then if you have no variable composition, that means all the molecules or atoms or whatever's in the substance are exactly the same as each other, then we have what we call a pure substance. And sometimes this is confusing, like water is a substance. Like, sometimes we think substance is a biology term, and it is, but substance can be a chemistry term too. So we can think of chemical substances as just a molecule or a compound or a substance. So like water liquid would be a substance, water solid can be a substance, water gas could be a substance, glucose could be a substance. And so a pure substance is having just one substance present. So usually a formula or an atom or a compound in a physical state. So, because you can imagine ice water. How would you characterize ice water? You have liquid water, solid water. Is that a mixture? I would say so. Is it heterogeneous in nature? I would say it's heterogeneous mixture, because the ice is at the top, the water's at the bottom. So an ice water sample to me is kind of fitting, over here in that heterogeneous mixture side. If I just had pure water, if I just had liquid water, no ice present, then I'm calling that a pure substance. So this might be just the water liquid. So just having a single molecule or compound or atom in its physical state, and usually just one physical state together. Otherwise, you have a mixture. If you have 2 physical states, even of the same substance present, then that would be some form of a mixture. And then the last question would be, is there more than one kind of atom present, or can you break that substance down into simpler components? And water you could break down into hydrogen and oxygen. And so the water sample we break down, actually I should write it over here because that's the compound side. So water we can break down into its individual elements. And so if we had liquid water, you could tell you have a compound because you can break it apart into its constituent elements. This is how the alchemists were determining different elements in the 16 and 1700s, is they were burning different sorts of ores and different sorts of minerals and trying to see what do you eventually get down to when you finally burn these things to the point where they don't break down any further. And then that's when you were getting things like iron that was discovered, zinc, and other metals that naturally form within ores and crystals that they were mining from the earth. So that was the early days. Just break things down until they don't break down any further. Then that's how you determine what makes something be an element. And then when those different elements have different properties, then they have different names, different substances, and different characteristics. And so then if you can't break down a substance anymore, maybe that's because it's already an element. So Iron solid could be a pure substance, so you have a metal that's shiny. Is it a single atom? You don't know until you put the molecular goggles on and you see only one atom of iron present, and then you can say, well, that's an element. And so does it contain more than one atom? It would be a compound. If it contains just one atom, then it would be an element. Okay, the thing I think that makes this box confusing is that one variable composition question, you have to know something. But variable composition is, if I look at one molecule versus another molecule, are they the same or are they different? So that's what the variable composition question is addressing. Let me throw this question to you guys. So which term here does not describe a sample of table sugar? So just imagine you have table sugar and it's something you put in your coffee, so it's nice ground up. So you look at it, it's a nice white solid. Think about this question. You can talk with your neighbors for a minute or two and try to figure out which answer you think here does not describe that sample. All right, so what do you guys think here? So probably not that hard of a question, but something on this question I think that is tricky is just like, how do you know what table sugar is? I mean, like we have to know a little bit. Like, is table sugar an ionic compound? Like, I don't think so. Table sugar doesn't have a metal in it, right? So table sugar is some form of carbon, hydrogen, and oxygen. You might remember either glucose, C6H12O6. You don't have to have that memorized. It's actually mostly sucrose, which is C12H22O11. But it definitely contains molecules. It contains the molecules of sugar, whatever those are. But you can probably picture there's some sort of molecule present that makes that a sugar. And then it's definitely a compound because you're talking about something that contains C, H, and O, different elements present together. That makes it a compound. So it's certainly not a pure element. The homogeneous question versus the heterogeneous question is tricky because the first one says, it doesn't say homogeneous mixture, it just says, is it homogeneous? Homogeneous is does it appear uniform throughout? And it does. It would just be white solid, nothing else in there. So it would appear to be all the same white solid. And so the sample would appear to be homogeneous. So hopefully it's not heterogeneous because we're down to that one. So hopefully by process of elimination, it's D. But heterogeneous mixture would be, there'd have to be like two different phases present. I'd have to see like one colored solid or another colored solid or solid with a liquid mixture above it. Something where I get two phases, two different colors. I don't see that within an ordinary sample or like what we would think of in a packet of sugar. So of course it's not heterogeneous. So again, probably not too tricky of a question, but I do like to give you guys a chance to kind of chat and kind of talk with your neighbors and try to answer questions or think about answers throughout class. So let's think about this question here. Isn't so much a question of which box answers the question, but can we classify in each box whether or not we're looking at an atom, a molecule, a compound, and or a mixture? So like which of those terms apply to the given boxes? So let's take box 1. So does atom apply? There are atoms in the box, but they're bonded together. An atom would be what I think of, is there just a single atom that's not bonded together? So it's maybe a tricky question that it's not atomic. So think of the question of asking, is the sample a single atom? And it's not. The atoms are bonded together. So the word atom would not apply to box 1. Would the word molecule apply to box 1? Of course, molecule applies because you see two different atoms that are bonded together. So molecule applies. And then the word compound, does that apply to box 1? Nope. And so another tricky part here is think of this, the coloring and the shading. So whenever I see two of the same shaded or colored atoms, that's implying the same element. If I see different shading or different colors, that implies different elements. So compound doesn't apply. And of course, it's not a mixture either. So the only word here that would apply to box 1 is molecule. Box 2 we can start mixture right off the bat, right? Because I see kind of like molecule 1, molecule 2. So I see a variable composition. So box 2 is variable. I don't know why I'm writing that, because it's just like makes obvious my handwriting's terrible, but variable composition is what we could say that then leads us to knowing that we have a mixture. And so we have a mixture here. Now, do you think it's heterogeneous or homogeneous? This one would be homogeneous. Now, that one's I think a little bit trickier, but think, is it like layered? Is all the one elements on one side, all the others on the other? Are they separated from each other? These boxes are kind of implying gases too, so you're almost like imagining that these like molecules would be in some sort of random motion bouncing around this container, so that would have to be homogeneous. Doesn't really ask it in the question, but that's a mixture, would apply. It's a mixture of molecules, and we actually have a compound present here too. So we have molecules that are present in this box, and then we have a compound. So this is our compound here. Let's call that A, and then molecules A and B, where B is like box 1, the molecule but not a compound. So we have a mixture of a molecule and a molecular compound. Box 3, which words would apply there? So not atom. I don't see a variable composition. We would actually say for like boxes 1 and 3, we would say they have a non-variable composition, which is just a long-winded way of saying that they have the same composition. So non-variable or non-changing composition. So therefore, this would just be a molecule and a compound, or a molecular compound. Box 4, what would we say here? So it looks like we have monoatomic gases that are present, 2 of them. So I would say I have a homogeneous mixture of 2 atomic gases. So we have atoms, we have a mixture, it's homogeneous. Why am I echoing? I don't know. You guys, did you hear that? Something like volume on something turned up. Oh, that's what happened. My iPad was playing the audio on a delay. It's never comfortable when you hear your own voice coming back at you like half a second later. Okay, so homogeneous mixture of atomic gases in box 4. Okay. Now, box 4, is it variable composition or non-variable composition? Variable, just 2 different things present, so it's variable. And then is it uniform throughout? That's like the homogeneous. So the homogeneous comes from its uniform. I still hear myself echoing. Okay, any questions? Feel free ever in class if you do have questions or something. Yeah. What would a heterogeneous mixture look like? It would just almost have to have all the atoms on like one side of the box and all the atoms on the other. Or imagine all the 1 elements are on one side of the box, all the other atoms are on the other. We'd have to probably get out of the gas phase too, so they'd almost have to be like in the liquid phase. Most of the heterogeneous examples are usually more things that you can imagine, like the oil and vinegar, like a salad dressing, something where like we could give you an example, like an egg, have a yolk, the shell, the white, something where you could picture and just know something by looking at it that it has that non-uniform nature. In terms of a picture in a box, I can't think of too many examples where we show you like an atomic picture like this, where it's heterogeneous, but it would just have to be the atoms like layered together. Good question. Okay, so let's talk about how we separate mixtures. So if we have mixtures, how do we separate them? This is just kind of a quick introduction to a few like lab techniques, some things that you'll see in the lab. Filtration is one technique. So obviously, if you had a solid and a liquid, you could separate the two just with filter paper. You'll do this in the lab a lot, especially if you take OChem, you'll do this a fair bit in that class too. So you can also take a liquid sample if it has two components, and if you could add something that would make one of the components turn into a solid and the other one stay there, you can then turn that into a situation where you can use filtration. So filtration is how we separate solids and liquids. We also have ways to separate two liquids if they have a difference in boiling point. So salt water, for example, you could have NaCl in water, and then you can boil the water. The water comes off more readily than the salt does, and so then you can trap, with a condenser, cold water, trap the purified water. You're just going to have to do this more than one time. You're going to have to cycle through. Your end stage water is going to have a little bit of salt, sodium chloride still in it, so then you redistill and keep kind of going and keep distilling until you get pure water. That's why distillation, like seawater, isn't a really good technique to do to purify it, because it takes more than one distillation. There's a lot of energy involved. You can distill water and ethanol, because ethanol has a lower boiling point. So the key that you need for distillation is two different substances that are present to have a difference in boiling point. So ethanol boils lower than water. So if we heat up a sample of water and ethanol, like think about heating up a wine type sample that has 10 to 15% by alcohol ethanol, and you want to make it stronger, probably more alcohol, then the alcohol boils first and is going to be higher in quantity in your pot, in your receiving flask after the distillation. This is probably the only time we talk distillation in this class is on this slide. You might see it in an example or two. You won't do a distillation in lab until probably OChem. So if you take organic chemistry, the lab, you'll probably get to do a distillation in that class. You'll do a lot of the chromatography also in OChem, but we'll introduce this here as a separation technique. We actually see this a lot with like black ink pens on paper that then get wet, and then the paper acts as a solid support for the ink molecules to travel through. And black ink usually has blue dye and purple dye. And so the two different dyes travel at different rates through the solid material. So column chromatography, or just chromatography in general, is where you have a solid material, think sand, think alumina, think silica gel, think a piece of paper, and then think about loading at the top of the piece of paper or material a mixture, and then the mixture just goes through the column at different rates. If anybody becomes an organic chemist, you start doing these things like once or twice a day, and they really annoy you, and it's a tedious task to do in the lab. But column chromatography is just how you can take a couple of components that travel through the solid support with different rates. So I'll let OChem kind of take it from there, because you won't see this as an example in lab. Probably won't even see this as an example in too many homework problems, but just want to plant the seed for the idea of compounds traveling through a solid support, where the solid support almost has like hands on it, and certain molecules have more or less hands to hold on to the solid support. And we can think of this also as like paper and ink, and we've seen examples of chromatography in our everyday life before. Okay, let's talk a little bit about energy. There's an energy unit in the chapter. Let me say right off the bat, if you look at the middle section in chapter 1 on energy, it introduces some math problems with energy units. We're not going to go through those math problems. We're just going to introduce the main ideas behind kinetic versus potential energy, and then try to relate them to like a chemistry example, separate them from the main physics example of the bicyclist at the top of the hill, and kind of compare and contrast what it means to be high in potential energy as a bicyclist versus a molecule or a compound. Okay, so we have a bicyclist at the top of the hill, high potential energy, right? Because they can start going down the hill. And I think we know from physics class or just from simple, physical science classes that you may have taken, that as a bicyclist goes down the hill, they are gaining kinetic energy as they're losing potential energy. Stored energy from being high on the hill is being converted into kinetic energy. So kinetic energy is the energy of motion, 1/2 mv squared. Again, we're not going to worry about plugging numbers into an equation and calculating kinetic energies. It's kind of boring. We'll bring up energy units when we get to chapter 5 and do more calculations with energy in that chapter. But we just want to then compare and contrast what it means to have a high potential energy in terms of bonding. So the balloon we blew up last time had hydrogen and oxygen in it, which are actually like the bicyclists. They were at the top of the chemical hill. because hydrogen and oxygen are actually, they have a lot of energy that they can give off if they simply have a spark and they can see the hill downward to form water. So hydrogen and oxygen are at the top of their potential energy standpoint. So they're at the top of the potential energy hill, and then you give them a spark, you form water, you go down the hill, you lose all that stored potential energy as kinetic energy. The kinetic energy we saw in terms of the kaboom that took place when that reaction had the candle hit the balloon. And so the nature is that we're changing the bond energies of what happens. We're taking the bond energy of the hydrogen atoms versus the oxygen molecules. We're taking that bond energy and changing it when we form water. We're actually forming more stable bonds because we started with less stable bonds. So it's all about relative bond energies. That comes up in chapter 5 and chapter 8 this semester. But whenever we change the nature of bonding, we can change the nature of the energetics of the reactants and the products. So some reactions will release energy like this one. We see a tremendous release in energy. Other reactions will take place where they actually have to absorb energy. And so those two different types of reactions, though, can still take place spontaneously. Spontaneity is an awesome question. Delta G, you might remember that. Who remembers delta G? Delta G is the spontaneity equation. If it's negative, a reaction can occur spontaneously without outside forces. If the delta G is positive, it can't occur without outside forces acting upon it. You see that in chapter 19 in Chem 1220 if you take the second semester. That particular equation is useful because if you see a delta G positive, all you need to do is apply energy. You apply energy, you can turn that reaction on that was non-spontaneous under normal conditions. Just apply enough energy, like in other words, take your battery, use it during the day, because that's a spontaneous reaction that's taking place without outside forces acting upon it. And then when you need to recharge it, that's what the charging port's doing. That's what electricity is doing. It's recharging the battery. That comes up in chapter 20. So potential energy is just the nature of the different bonding environments, reactants versus products, and we can have a change in potential energy. And if we have a loss of potential energy, we can see that like the hydrogen-oxygen balloon given off in the form of energy, in the form of heat in the terms of the fireball that took place. Let's just get a quick look into some of the mathematics. This will feed a little bit into the activity that you guys are going to do in recitation before we get back Wednesday here and lecture and have another lecture. Monday, of course, is a holiday. Maybe the non-native students who don't know Labor Day. Labor Day is Monday, so we have off school, so it's nice to have a nice Monday holiday after our first 4 days of class with awesome weather and an awesome, hopefully, game tomorrow. But let's talk units real quick. These are the prefixes that we're going to convert to and from and just need to be able to use. And so I wanted to introduce that this side here is getting at smaller units. So like 10 to the minus 2, 10 to the minus 3, 10 to the minus 6 for micro, 10 to the minus 9 for nano. The prefixes do continue, but those are the prefixes that we're going to use the most. And so let's think milligram. There's like 1,000 milligrams in 1 gram. So 1 gram has a lot of the little milligrams. We can also divide both sides by 1,000 and say that 1 milligram is a 10 to the minus 3 gram, or 0.001 gram. So we can relate conversion factors one of two ways. We can either say how many milligrams are in a gram, or how many grams are in 1 milligram. So you can always give conversion factors one of two ways, but the key is going to be trying to know how to give those conversion factors, and use them for milligram conversions, milliliter conversions, et cetera. So we're gonna have to memorize, or just remember, hopefully, milli is 10 to the minus 3, micro is minus 6, nanos 10 to the minus 9, centi 10 to the minus 2, and then on the bigger side, we have 10 to the plus 3, 10 to the plus 6, 10 to the plus 9 for giga. And so I'll save the example for later. I want to bounce and just look at a couple other things before we leave here today, just to kind of start planting a few seeds. Let's briefly get into a quick little discussion of sig figs that hopefully we can build from on Wednesday and just start thinking about what sig figs are and why we talk about them and their importance. Like whenever I take a measurement in the lab, and we do this all the time on a balance with a graduated cylinder, like we use a graduated cylinder to determine volume, and I say, it was filled up to the 10 milliliter line, so I have 10.0 milliliters of liquid. Like that's a different number than if I used a more precise tool like a pipette or some other sort of device, and I say I have 10.000 milliliters. So the difference between these numbers is the extra zeros mean the second number has more precision. We say it has more significant figures. So the bottom number has 5 sig figs. The top number only has 3 sig figs. So the more sig figs, the more significant digits, the more digits you know a value has through measurement, the more precise you know it. But then the problem comes, well, whenever we start doing calculations, if I do a calculation with 10.0 milliliters versus 10.000 milliliters, it might make me round my result differently. It might make me have a different confidence in my result. But now then there's also a lot of things that aren't subject to sig fig rules. Like I could count 1, 2, 3, 4, 5 students in the front row on this side of the room. I know there's 5 students over here. That's not like 1 sig fig. That's a perfect count. So whenever I can count something, whenever I look at a conversion factor, those are precise and exact. And we know those for sure or by definition or by counting. So sig fig rules only apply to those ordinary lab measurement, the inexact things that we measure that we're trying to then later do calculations with. So we'll build from this next time. We'll stop here for today. You guys have a great weekend. Enjoy the game. Go Buckeyes.